Thank you for the introduction. It's a pleasure to have you all here. My name is Seunghyun Lee. I'm a postdoc in Professor Philip Wong's group at Stanford University. Today I'll be talking about NEM relays using two-dimensional nanomaterials for low-energy contacts. We would like to focus on materials and interfaces. If you look at any nanomechanical relays, you'll be able to see that there's always hysteresis. The pull-in voltage and the release voltage is always different. That's because when these mechanical structures make contacts, there's additional adhesive forces that prevents it from being released at the same pull-in voltage. Now we can scale down these nanomechanical relays. We can scale down the power, the voltage, and the dimensions, but the adhesive forces between these contacts cannot be it's not always linearly scaled to the dimension. So just like transistors, when we scale down the gate length, we are thinking of using different materials for different reasons. We are thinking maybe there are some other materials out there that can be used to make contacts in nanomechanical relays. One of the most obvious candidates would be van der Waals materials. These are typically layered materials with a strong atomic bonds in the x and y direction, or in the z direction, there's only weak van der Waals interaction. One of the most popular example would be graphene, which is essentially a single layer graphite. There's also traditional metal dichalcogenides, such as molybdisulfide, that Professor Feng and Professor Zave talked about yesterday. There's also carbon nanotubes. Now, carbon nanotubes are, strictly speaking, not two-dimensional materials. However, they're essentially rolled up graphene, the same atomic bonds as graphene. Now, if you look at these three different materials, graphene and carbon nanotubes have the same atomic bonds, but different dimensions. Transition metal dichalcogenides, such as molybdisulfide and graphene, they have the same dimensions, but they have different atomic bonds. Now, they all have three different band structures. For example, graphene is a semi-metal with zero band gap with linear dispersion relationship. However, molybdisulfide is a rather large band gap material with about 1.9 eV band gap. And carbon nanotubes, depending on the chirality, can be either metallic or semiconducting, and different band gap depending on the dimensions. So what we would like to look into is the nanoscale interfaces formed by different atomic bonds, band structures, and dimensions, and really compare what's happening at those interfaces for different materials. Now, we successfully made graphene, a standalone graphene beam relays with nickel as sacrificial layer. So this is the SEM image of the graphene beam relay. What we observed is that we successfully observed the pull-in voltage, but it was difficult for us to look into the release voltage. And I saw Dr. Feng; he actually had a graphene beam relay which was released. But for us, it was not so easy to see the release of these graphene beam relays. This we think is mainly because of these atomically thin structures. There's really limited restoring forces after contact. Although if you design in a certain dimension, we may be able to see a release of the structure. However, as we scale down, we would want the adhesive force to be as small as possible, but the restoring force to be as large as possible. So what we thought is, why don't we exploit the surface properties of these nanomaterials, but still use a traditional mechanical structure to have a higher restoring force, so that we could possibly eliminate hysteresis or even hysteresis and the difference in the pull-in and the release voltage. Now, I've been working with graphene for quite some time now. Graphene as a mechanical contact material is quite excellent. It has big van der Waals interaction with very little dangling bonds corresponding to low surface energy. Its Hammocker's constant is about an order of magnitude smaller than most materials. This is related to the van der Waals between contacts. It's highly thermally resistant. It will prevent micro-welding, which can happen with metal electrodes. Graphene doesn't burn or react easily at high temperature. It's a very good thermal conductor. It's also a good electrical conductor, and it could withstand regular current density. In nanoscale, it's the highest mechanically strong material, with strong carbon-carbon covalent bonds. It also acts as a surface passivation layer to reduce metal oxidation. Graphene is a barrier for oxygen. And it's also resistant against humidity. Metal can be affected by humidity. It can be oxidized. For graphene, water molecules and oxygen molecules really just act as dopants. It's also low cost. It's much more common than hard rare earth metals and silicon carbide used in MEM relays. Large area synthesis is possible with CVD method. And most of all, it can be transferred in room temperature to any arbitrary substrate. So I've looked into some of the low energy materials and wanted to look into how good is this graphene as a contact material. So I looked into a figure of merit called Peel number. What Peel number is it's the ratio of the elastic restoring energy versus the contact, the surface adhesive energy. And we see that as if the ratio is higher than 1, that means this cantilever can be released. But if it's under 1, that means it will still stick. Now, if we compare different materials, you can see that graphene, the red line, has a much better, much higher appeal number compared at the same leg length. This shows that graphene is a good material with very little surface energy and adhesive energy. How about molybdisulfide? Molybdisulfide is monolayer TMDs are the thinnest material known to have band gaps. Like graphene, high on-off ratio, low off-state conductance, a direct band gap, strong current saturation behavior. And similar to graphene, it's extremely thin. There's several integration options with CMOS. It also has potential for unconventional electronics such as stretchable and flexible substrate. This is an example where they use an exfoliated molybdisulfide made a drum structure, which is quite different from a switch, but they show the mechanical robustness. But as you see, most of molybdisulfide works focus on exfoliated samples. What we did is we can't really make there's additional fabrication difficulty with MEMS structures. Now, if you have an exfoliated structure, that's going to be extremely difficult to make working devices. So what we are focused on is making large area molybdisulfide. We use the in-house CVD method. We have the inner tube for controlled gas flow, baffles to trap sulfur gases. And you can see we have very colorful pictures. We use all the same substrates for all different recipes. And we have all these different colors, but we don't know what these are. So traditionally, just like graphene, you can use Raman spectroscopy, but these peaks, although they look similar to moly trioxide, they're not quite moly trioxide. So we did some OJ spectroscopy to see what these specks or these dusts are. So if you look at the elemental composition, the lighter the color, the higher the composition. So we have less sulfur, this area, similar molybdenum, and a lot more oxygen. So we know these particles are actually moly trioxide. Okay, we've successfully synthesized a large area of molybdisulfide film up to a centimeter by centimeter in size. We've confirmed with Raman signals. Just E1, E12G, and A1G are the representative peaks of molybdisulfide. We saw that random locations. We have monolayer film, a uniform monolayer film on the whole area. Also,
I missed that. You started with molybdenum oxide.
Molybdenum trioxide. It's sulfur.
And the sulfur actually reduces or replaces the oxygen?
Yes. And so now we have a means to make a large area 2D material. So we designed with the concentric drum structure, varying area, and actuation contact area. We have additional body terminal to control the pull-in. We want to experimentally investigate the adhesive relationship between adhesive force, hysteresis, contact materials, and the contact area. So anybody working with graphene knows it's not trivial. Processing graphene is not trivial. This is a double-edged sword. It has low surface energy, so it doesn't stick to the contact, but it also doesn't stick to the surface substrate as well. So and graphene tends to form three-dimensional material. If the van der Waals interaction is weak, it tends to roll up. So we tried on different substrates, aluminum oxide, metals, with HMDS, plasma, silicon nitride. What we found out is there's several factors. The surface energy, the roughness, hydrophilicity, hydrophobicity that affects the adhesion. We know that in this sequence, metal, silicon nitride, aluminum oxide, and silicon dioxide, in this sequence, the graphene sticks better. And also HMDS doesn't work well because weak interaction in the SAM. And also, but the plasma works better for most surfaces except metal. It looks like plasma actually oxidates the metal. Now, going back to the one-dimensional material, which has the same atomic mass as graphene, we have a new postdoc, Ji Kao, who's been working on this CNT. Now, the problem with the CNT is the exact positioning and alignment of these materials. She has been working on this two resist method in direct electrophoresis to place carbon nanotubes on a designated location. And the result is that we have highly aligned, high-yield carbon nanotube arrays. We have high yield, error of sub 50 nanometers, and adjustable density. And G also successfully fabricated 3-state mechanical relays. Now, one of our goals is to make a 6-terminal relay such as this. If you look at closely, this is actually an inverted Azor gate. Which is, we only have 6 terminals to make it, and it's pretty simple to make an inverted Azor gate if you look at the gate. So as a summary, I demonstrated a graphene-based beam relay. We showed how layered van der Waals materials can be good interface materials. We looked into the CVD synthesis of large area transition metal dicalcinide, designed the concentric drum relays for experimental verification. We were focused on graphene transfer and also showed the status of carbon nanotube relays. I would like to acknowledge the Center for E3S Center for funding, and also the Swiss Nanoterra project Capturus, and also the Project NanoRF and the Swiss National Science Foundation. Thank you.
Do we have any questions? Yes.
Hello. Hi.
Yes.
Thanks for the wonderful talk.
Thank you.
In particular, I'm interested in the CVD process that you used for large area molybdenum disulfide.
Yes.
Were you able to get a single crystalline layer, and how did you determine whether it's single crystalline?
Of course not. It's such a large area. If you get a single crystalline layer, that's amazing. I think some of the records are about several tens of micrometer in size.
Grain size.
We know it's polycrystalline. We are thinking of collaborating with the molecular foundry in Berkeley to look at the film quality and the grain size. Yes.
Okay. Yes, you are.
So I've heard of Reynolds number. I never heard of Peel number. You think that when they sell Scotch tape, they should include the Peel number. So I'm very fascinated by that. But overall, it seems like you're suggesting we should make electrical contacts with graphene. Earlier, we heard a suggestion we should make electrical contacts with silicon carbide. All of these things are kind of similar, and it's hard for me to believe that they really overcome the problems that they stick and they erode and they have reliability issues. So why should I believe that a graphene contact, I don't even know what you're contacting on the other side, actually. Why should I believe?
Yes.
Yeah. Why should I believe that this is a better contact?
Okay. Now, silicon carbide. I talked about several advantages. A lot of the hard materials, rare earth metals, and silicon carbide, they're expensive. That's one thing. Another thing is that in Dr. Feng's paper, you actually saw a release of graphene relays. Now, if you think about the restorative forces of a one atomic sheet, that's extremely small, but it still can be released. Now, other structures are beams. They have a much higher restoring force, and they still release. But if you look at hysteresis, it's in a similar order. What that shows is the actual adhesive energy of these graphene is actually much smaller because the restorative forces should be much smaller in carbon nanotubes and graphene. So if you use the mechanical robustness of a traditional MEMS structure and have the contact made with these graphene, which I don't think anybody have ever done, we may actually reduce the hysteresis by a great amount. And that can be very helpful in reducing the overall scale of these nanoscale devices.
We have time for probably one more question. Well, if not, let's thank our speaker.